Now, let's solve the same truss, the same bridge, with method of sections. The previous one, which took us 40 minutes, was method of joints, but trust me, as you practice and practice, you will be faster and faster. I was explaining a lot, so it doesn't really take 40 minutes, it takes 35 minutes. So, method of sections. Method of sections is very similar to method of joints, but as we discuss it through the slides, it is perfect if you want the forces in a specific joint member or truss member. The question, imagine currently, is asking us what are the forces inside the member EB and BC. So it doesn't care about the other ones. It says, okay, tell me what are these two and I will sort out the rest. So one of the steps of method of joints is very similar to method of sections. Initially, you just figure out what are the reactions. So again, I have a pin here and a roller here. Because it's a pin, I had RAY and RAX. And because it's a roller, I have an RD. Can I figure these out? Similar to method of joints, that we consider the whole thing as a solid body and we started calculating every single one of the reactions, we do the same thing as well. We have already done that, so I'll just bring out the calculation that we did. So exactly similar to what we did here, which we considered the body as a solid, and then we calculated RAX, RAY, and RD. We will calculate here as well. So let me just write RAX is equal to 0, RAY is equal to P, and RD was equal to P. So all of these was calculated, considering the entire body as a solid and using the three equations of equilibrium. Now that I have these unknowns of reactions known, I just concentrate on the members that I need to figure out what are their actual forces. Through method of sections, you can cut the sections, you can cut the members into half as long as you do not pass more than 3 members. Whichever member you cut, you can simply calculate what are their actual forces, whether they're under tension or compression. If I want this member and this member, do you accept that if I cut like this, I cut my entire truss into two halves, left and right. If I separate this bit, so the right goes to the right, the left goes to the left, I will end up with something similar to this. So I have used the method of sections to cross. So I cut through the members of interest, but not more than 3 members. Yeah, I was interested in BE and BC. I cut through them and I made sure when I cut, I don't cut more than 3 members. I know FE is cut as well, but I had no other way of passing through these two but not passing through FE. You see, I could have cut it like this as well, but then it would be 1 member cut, 2 member cut, 3 member cut, 4 member cut. No, but this is only cutting through the members that I'm interested in, perfect, as well as a third one which I was forced to, but not more than 3 members. Now I have the left side and I have the right side. So these forces that we are looking at are internal forces. So for this, all forces, direction, will be intention, meaning it will come out. So whatever I cut, I'll put an arrow at the end and it comes out. Do you accept that this is FBC? Do you accept that this is FBE? I'm just cutting it, so whatever I cut it from here or here or here or here or here, inside it is always FBE or FEB. Doesn't matter. We discussed it, that's the name really doesn't matter. And then FFE. So the same thing happens here as well. Let's say if this is alpha, I can even write the components of this guy. This will be FBE cosine of alpha, and this will be FBE sine of alpha. So I cut it through the members that I was interested, not more than 3 members. I bring it out and I draw all of the forces in tension from the points that I cut for both sides. Now to solve it, I'm interested in what is FBC and FBE, BE and BC. To solve it, wherever I cut it, I'll consider the rest of it as a solid. Similar to what we did to figure out these guys. Do you remember? We said, okay, the whole thing is now solid. I have a force P here, another force P here. I have RAY, RAX due to the pin, and RD due to the roller. And I just solved it to get the reactions at support. I do the same thing here as well. The only difference is now I have some forces on one side of it. Imagine I cut it from here, P and force P, and then I solve it. Okay, let's solve it for left hand side. Solve for left hand. By solving, I mean let's write the equation. Summation of all forces in X, this is my positive direction. Remember, I'm just considering this side. Will be FBC plus FEB FFE, FBE, FBC plus FFE, both of them in the same direction. There is a cosine alpha here as well, so plus again FBE cosine of alpha equals to 0. Okay, one equation done. Let's see whether the others will help me solve this. Summation of all forces in y direction equals to 0. Going upward is positive. What does that give me? I have an RA here. So let's say, let's put RA here. From here, RA, which was equal to P. So RA, I have this guy, which again is going upward, so plus FBE sine of alpha, and I have this P which is coming downward, minus P equals to 0. I know that my RA is P, is equal to P. I have already calculated it in the beginning of the previous one as well. I was calculating the unknowns of reaction. This is known, this is known. The only unknown is FBE. Can I solve it from here? Yes. So P minus P is 0. So from this, I can conclude that FBE is equal to 0. If FBE is equal to 0, then this guy is equal to 0 as well. Let's keep it for there. Now let's do a moment along one of the points. Let's say we were usually doing it along point A, but I have lots of knowns over there. My unknown currently, FBE, is known, so these two are my unknowns. Let's do it through point B. Remember, you can do moment along any point that you want. Let's do summation of all moments along point B, and this is the direction positive. Again, remember, this force is actually coming from here, so although I have drawn it with a distance, this distance is nothing. This force is along the entire of the member, so it's actually coming out of here, and this force is coming out of here. So any force which will affect on B should have a distance parallel to it. I can see this guy having a parallel distance, and I can see this guy having a parallel distance. If this is going around point B, let's highlight it, point B, it will going around it like this, like clockwise. So let's say RA times its distance is L, the parallel distance of RA to B is L. The same thing happens here. Look at this, FFE. If it goes around point B, again is clockwise. And what is the perpendicular distance of FE to B is this distance. Again, this FE, although I have drawn it here, is actually coming from this point. So the distance between F and B is the parallel distance to generate M equals FD. Yeah, so this thingy, which I had the force and I had the distance, M equals force times distance. The distance of this force to point B that I'm generating a moment, which will be clockwise following the arrow with the center of B, will be L, and it is clockwise, so FE times that distance, which is L. So RA times its distance, which was L, and FFE times its distance, which is L, equals to 0. Again, RA, I have already calculated, this is P, similar to here. So can I conclude from this that FFE is equal to P, because this L with this L goes away, this goes to the other side. Yes, I'll put it as a negative P as well, because if I take this to the other side, this was positive, this was positive. If this is P, P goes to the other side, negative P. So FFE is negative P. That means that this direction that I have considered is wrong. The negative sign indicates that the assumed direction is wrong. So if I consider it to everything to be tension, this means it is in compression. But now, having FFE, can I write here that this is negative P? Doesn't that conclude FBC is equal to P? So now I had this, I have this, and I have this. And it's a positive, so this is in tension. And FBE is generally 0. It's a 0 member. Did I solve everything? Yes. And if you remember, in our initial consideration, this one was in tension, which is in tension, and this one was in compression, That's why it came negative. And then because I assumed in the beginning in the method of sections that is in tension, it says it's wrong. This was from the method of joints. So this member is under compression, this member was a zero member, and this member was under tension. BC is equal to P. So the solution of the entire of these two members through method of sections was to just cut the section wherever you want, divide it, assume all of the loads coming out in tension, consider one direction of it, we consider the left hand side. Trust me, if you do the right hand side, the same thing will come up as well. And just solve it with the three equations of motion that you have. You might ask, why not put the moment along point A? Let's do that. So summation of moments along point A equals to 0. This direction positive. I will have a P times the distance, and it's going around A in clockwise, so it's a positive P times L because the distance is L. I will have this guy going around point A again clockwise, so it will be a positive FE times its perpendicular distance, which is L, and I will have this guy, because this, if I put the forces here, again we said doesn't matter where, but if it's here, the perpendicular distance of FBE, cosine of alpha, the distance is 0 because the force is here, there's no perpendicular distance. But this guy, you see, I can go around A and the distance is L, but this time if I follow the arrow is negative, so it's negative FBE sine of alpha times its distance, which is this much, L, from here to here, times L equals to 0. I have already calculated that from here this is 0. Don't I get the same result? This will go. FE is equal to negative P. The same thing that I did. So trust me, if you get a moment along any point inside this, you will get the same results. I didn't do A, I wanted to do B, so you see that there is another way as well. And then remember this, by doing through point B, I got rid of one of the unknowns, because B will get rid of these two, they're all from here. So it was a smarter move, and it was faster. Anyhow, speed is important as well. But the entire of this calculation was about 20 minutes something, and with all of this description and going through it. But trust me, in a normal situation, if you use the method of sections, it won't take you that long. It will be very, very quick. So we had the method of joints, we had the method of sections. And depending on the situation, if you need to analyze every single actual force in every single member of your truss, you don't have any other options. But if you just need limited number of actual forces in limited number of members to be calculated, then method of sections is the best one. You just have to cut the section into two halves, but that cutting should not go through more than 3 members. And then the moment that you cut it, one side you will consider it. We consider the left hand side here, and we will forget about the right hand side. We consider every single force coming out of the cut members in tension. As you can see, they're coming out, and then if they're negative, it means that they weren't in tension, they were in compression. In this case, one was correct, it came out positive, so it was in tension. One came out negative because it was in compression. So thank you very much. That was for this tutorial. There are some problem sheets as well, so please go through them and practice these methods, both method of joints and method of sections. They're very useful, and generally trusses are very common structures and you have to know how to analyze them. Thank you very much and see you later.